All right, Physics 3030, the Universe, Lecture 3. This is the second lecture about astronomy. And we are going to continue our discussion of how we measure the distance to different stars out there and different objects. And we'll be talking about the inverse squared law, which covers a lot of different laws in physics. And we'll use that in conjunction with something called luminosity distance to measure how far away these things we call standard candles are. And standard candles are just special stars, special types of stars that we know the properties of that allow us to measure how far away they are. And then we'll get to electromagnetic spectra as we keep moving along here. So let's close that ink layer and move to a clear page. Let's see what we get here. So we're going to start talking about inverse square laws. We talked a little bit in the last lecture about when something is inverse, you get the properties that you get as something goes up, something else goes down. And for these laws, there's an easier way, I think, to think about it, at least to start with. And these all have to do with something that either has a spherical source. And this also works for something that is a point source, but this is just a point source is really just a physics toy about the way we think about things, just starting in a tiny little point. But really, most stars out there can be thought of as spherical sources, okay? And there are other things besides sources of light, like stars, but let me just start drawing a picture here. I think this will make it a little bit easier. So I have some ball that's a source for something. And in our case, we're really going to be thinking about light. Okay, so let's think about light emanating from this thing sort of in all directions, right? As a sphere of light coming out of it. Okay. Well, as that light expands and comes away, it actually gets some part of it spread. So not some part of it. It all spreads out as it goes, right? So at any given instant, say there's some type of explosion or something like that, okay, then it's described by this big sphere, okay? And this could be the wavefront of a sound wave that started at a point. This could be a supernova explosion, or it could just be the normal light that's coming off of something. It doesn't have to be some specific event. But as it comes, it spreads out, and the area of this thing is the surface area of a sphere right, which is, so the surface area of a sphere is 4 pi times r squared, okay, where r, right, is the distance from the thing in the center, whatever it is, to the outside of that sphere. So you notice that we got the right units here, right? R is going to be in meters or whatever, maybe light years, but squared gives us a unit of area, and 4 and pi are just numbers. Okay. Now, the power that you get that comes off of this sphere actually goes like 1 over the area. Which is to say that if I'm really, really close, if I'm really far down in here, let me change color again. If I'm really close in there, that's a lot of power, right? A lot of power. It's like being at the surface of the sun, right? Imagine this is the sun, and you're at the surface of it. Well, you don't want to be at the surface of it. But as you come out, as you move out here, the same power is spread out over a bigger area, right? And this is something we call intensity. So the intensity equals the power divided by the area of what we get, okay? And that is to say that the further away we are, the more area, the bigger the area we're dividing by. And notice that the area is a 1 over r squared. Okay. So this is the idea behind these inverse squared laws. Okay. So it goes like the area of one of these spheres. As the sphere gets bigger and bigger, you're spreading out the power over more and more. It's the same thing as a wave. If I had a wave of water coming or something like that, as it would spread out, it would lose more and more power. Okay. This is exactly the same as thinking about, say, an air horn. Okay. If I was right next to an air horn, so some air horn that's giving out sound waves, right? This is on top of one of those aerosol cans, right? And if I was right here, man, that would hurt. I would not want my ear to be right there. But if I move way out here, so that's maybe 100 feet away, by the time I'm out there, that same sound is spread over a much bigger area, right? So this area is bigger. Okay, and so this is the same idea. And in fact, if I move double the distance, means I get a quarter of the intensity. And this is something really important. It doesn't go off. It's not linear, which would mean that if I doubled the distance, I would go half of the intensity. It's because of this r squared up here. Because of that r squared, if I double the distance, I get a quarter of the intensity. And this is really important. And just knowing this will allow us to calculate a lot of things, but this is really important for just sound, right? You get away from something and it gets that much quieter. Okay. And let me clear this board here. When we talk about this stuff, we're going to refer to it, the light coming off of a star, as the luminosity. Okay? And this is really just the power that comes off in the form of light. Now that might be a little confusing, but think about it, right? Think about a 30-watt light bulb. You guys have all probably held a 30-watt light bulb in your hand. And what is watts but the units of power? So that's what that says, is that you get 30 watts of power coming off of that light bulb. And so that's the luminosity of the light bulb. It's the same units, it's in watts. Okay? And we will often compare things to the luminosity of the sun. Okay, this is L sub dot. So when you see this is the luminosity of the sun. And just to be able to compare, the luminosity of the sun is 3.8 times 10 to the 26 watts, which is roughly about 10 to the 26th light bulbs, which is a lot of light bulbs, which is good because that's what we need the sun for. The sun is the engine of the entire Earth. So it's good that it's putting off that much energy for us. But thankfully, that's spread over a huge area by the time it gets to the sun. We wouldn't want to be getting all of that energy, right? This is the energy coming off of the sun in all different directions, right? And remember that as we talk about these things. Okay. Okay, so the one thing that I want to point out here is that this inverse square thing, this inverse square law, really works for all kinds of physical laws. So inverse square again here. And it works for all kinds of physical laws. So we already talked about luminosity and intensity, and that really, those are words that work for any kind of wave. So light, it works for, and sound, it works for. So these inverse square laws also work for sound, where you have something coming out of an air horn. But it also works for forces. And so there's one force that we'll talk about a lot, which is the force of gravity. Okay, and I think I may have mentioned this before. It's G, which is Newton's constant, Newton's gravitational constant, times the two masses you're talking about over r squared. Okay, and there's that r squared popping up right there. And so it's that 1 over r squared, so this thing, it falls off. The power of the gravity falls off as 1 over r squared, and it really does have to do, this is really for two sort of spherical masses, right? It really has to do with two spheres kind of pulling back and forth at each other with gravity, okay? And it actually is also true for the Coulomb force, which is the Coulomb force is the electrical force, and that's another constant times Q1, Q2 over r squared, where now these are the charges, and there is that 1 over r squared again appearing. And so we get it because they have these point sources, these little point particles that are really the symmetry of them is spherical is what we say. And because it's this spherical symmetry, you get this 1 over r squared exactly because the surface area of the sphere goes like 4 pi r squared. So that's the take-home message here, right? Is that things fall off like 1 over r squared. Okay, and we'll show you how to use that to calculate how far away something is. Okay, so let's clear the board. And the idea, the trick that I want to talk about in using these things is that we can measure the relative luminosity of a star really easily. So there's something called relative luminosity. And all this is the power we measure. Right? And so what we can do is do something like count the photons from a star. Remember this now, this is going back to the particle-like light. Count the photons from a star that hit a photographic plate that we put at the end of our telescope, right? So from the telescope. Okay, so you count those number of photons, you count the number that hit per second, and that tells us the luminosity of the star where we are. Okay, so relative luminosity is easy to measure. We can measure it for every star out there. Easy to measure. But we don't know, so now let's draw a little picture here, right? We don't necessarily, we have some star that's out there, and by the time it gets to us here on Earth, okay, this is us, maybe I'll draw us looking. Okay, by the time it gets to us, there's some power that we see when it reaches us, okay, moving in this direction towards us. But we still don't know what the power of the star is. Now, if we knew what the power of the star was, we could calculate the difference between the luminosities and know what was going on. But for some special stars, so the trick is for some special stars, we know something about the luminosity. We know the luminosity, the actual intrinsic luminosity, the intrinsic. something about what the luminosity is exactly at the surface of the star. Now, this is not something that we know the luminosity of our sun because it's so close and we can measure it and we know what kind of star it is and yada, yada, yada. But it's not something you know exactly. But it happens to be that there are some stars out there that you do know exactly what's going on with them. And so let's look at one of those guys, one of those types of stars, and it's called a Cepheid variable star. Okay, and this is a graph of, oh man, what's going on here? Let's see if I can get rid of that. Okay. So Cepheid variable stars, hopefully it doesn't appear again. And these were discovered by, well, they weren't discovered by her, but she found what's called Leavitt's power law. So Henrietta Leavitt, who was working at the Harvard College Observatory. And this is back in, I think, 1915, I want to say, maybe 1916, somewhere around there. She was working at the Harvard College Observatory. She was looking at all this data that had been collected. And this is one of the first times anyone had really noticed that what happened is the apparent brightness, right? So that's what's being measured on this graph here, is how bright the star is. Okay. Had some correlation with how often it peaked. Okay, so that is to say, there's some period here, so I can measure from this bright spot to this bright spot. Okay, and what happens is the way these stars work is that they go through dormant periods where they're just letting off, shining a little amount of light, and then they go to periods where they shine, lots of light comes out of them, right? And it has to do with the way the chemical reactions are going on, the nuclear reactions in the sun, and then they go back to only shedding small amounts of light, right? So this is there, this is the peak, and then this is back to this spot here, okay? And it turns out that their peak brightness, their actual, what this peak relates to, so this between these two times is what we call the period, capital T. So the distance between the two peaks, so the time between the two peaks actually relates to the total luminosity. So we relate, maybe I'll not write in red, relate. Now, intrinsic luminosity, this is a graph of the apparent luminosity, but it turns out that this actually is true for the intrinsic luminosity. So we relate that to the period. Now, once you know this for one star, it turns out that it's true for all of these Cepheid variables. So what the idea is because I have something that I can relate that has nothing to do with the apparent brightness. In other words, I can look in a telescope and it's easy to tell. It goes from bright to dark to bright to dark to bright to dark. It's easy to tell the difference between those peaks. Okay? And since I can easily tell the difference between those peaks, I can tell you what the intrinsic luminosity of the star is. Okay? So Henrietta Leavitt finds this out in the late teens of last century, and then immediately we get to start using this. Okay, and it turns out, if you're curious what the relationship actually is that it's a direct relationship, right? So as the period goes up, so does the brightness. So the bigger the period, the bigger the intrinsic brightness. And then we use that to compare the luminosity that we see in the star to the luminosity of the star that we know. And since we know that it falls off, right? Remember that it falls off like 1 over r squared. We can just plug in some numbers into that 1 over r squared to tell how far away the star is. Okay, so there's one other kind of specific star that I want to talk about, And let's move to the next page here. And they are called type 1a supernovae, novae, however you want to pronounce it. Okay, so type 1a supernovae, and these are, for those who don't know, you probably all know that supernovae are stars exploding, which is pretty cool when you think about a giant star exploding and releasing tons and tons of energy. But these are really, really important types of stars. They're really dense stars that need to be with a companion star, and the one star trades off a bunch of material to the other star. You have this little tiny compact object, and you have some big giant red star that sort of loses material to the other star there, and they're kind of rotating around each other. Crazy setup here. And they just kind of orbit around each other. And at some point, this tiny little star, which is a neutron star, really dense star, gets enough stuff from this one that it just explodes in a huge supernova. And we might get to the details when we start talking about stars much later in the course. But the important thing is that if you looked at a graph of one of these supernova, and you looked at the flux, which is what we measure, that's actually what we call the number of photons, right? So this is sort of number of photons per meter squared that we can measure. So this is what we actually measure on a photoplate, which I can actually write as watts per meter squared. I guess centimeter squared is a popular unit too. So anyways, the flux over time, right, what ends up happening is you get the explosion, comes up, and then drops back down, and it takes a while to tail off, right? But, so this is the flux that we measure, but if I were to write this as just instead of a graph of luminosity, now this flux, so remember, flux is really what we're writing in those equations, is the total luminosity that you get from the star, right, where it would, so this is the luminosity at the surface, sort of, so this is the power at surface. And you got to divide that by the area of where you are. So instead of writing now R, I'm going to write D, where D is the distance away. That's the distance away. This is the equation that we can actually use to calculate things. Okay, so this is the distance it is away from you. This is L. Now, if I were to write this graph L as a function of time, right, whereas this upper one changes with distance. The amazing thing about these supernovae is that this peak is always the same luminosity. Okay, so let me go over this again. What I'm saying is this upper graph is what we see in our telescopes, okay? And this is what's actually happening at the surface. What happens at the surface? And what happens at the surface is it always releases the same amount of energy, always releases the same amount of power every single time. And because this type of star, is so exact, makes it really easy for us to be able to tell how far away they are. And these are actually much more powerful than those Cepheid variable stars. And we'll talk about these much later when we start talking about dark energy near the end of the course. But I wanted to introduce it here because it's the same type of thing and the same type of calculation that we want to do. And of course, using this equation up here, flux equals the intrinsic luminosity times 4 pi over the distance something is away. This is the equation that we'll actually be able to use to calculate stuff, to calculate actually the distance something is away, right? So we're always looking for this D. So we can, if I know the intrinsic luminosity of something, and I tell you its flux, then you can just solve for D, and if we do all that, we're going to have 4, let me do this in a different color here. solving for d, it's going to be 4 pi times f. And trying to do it in my head here, so let's see. Put the d up there, upstairs, L downstairs. Okay, so the intrinsic luminosity over 4 pi f is equal to the whole thing square rooted, right? So there's your calculation. If someone tells you the flux and the intrinsic luminosity of something, you should be able to tell me how far away it is. And you'll definitely have a problem like that on your homework. And maybe on the quiz as well. Okay. The last thing that we're going to talk about is the electromagnetic spectrum. And I'm just going to show you a couple of pictures here that sort of sum up what's going on. This is a picture of the electromagnetic spectrum. What we know about light, okay, is that for any type of wave whatsoever, so this is all waves, I'll write this first one here, all waves obey this equation, that is the velocity of the wave is equal to the wavelength of the wave times the frequency of the wave. Okay, where this is, you have some wave going along here, right? And the wavelength is the distance between two peaks or the distance between two troughs. That's the wavelength. We use often the Greek letter lambda. That's the wavelength. Okay, and the frequency is how often these peaks pass by you in time, right? And so if something is passing by you faster and faster, then you have something that has more and more humps to it, right? And you see that there's actually a relationship between the frequency and the wavelength. The wavelength gets smaller when the frequency gets bigger, and frequency, again, is the faster something happens. Now, for light, it's the same equation as up here, right? But since we know we have a special velocity called c, that equals lambda times f. So the frequency, the symbol for frequency is f. Okay. So this relationship is a great one. We know that c is a constant. At least out in outer space, it's always a constant, right? It can be slower when it has to move through glass or something like that, but we won't talk about that here too much. So these two guys, frequency and wavelength, are in an inverse relationship, right? C is a constant, so if lambda goes up, frequency has to go down. And if lambda goes down, frequency has to go up. Okay? And this is a very important relationship for you to remember, and will definitely probably make you manipulate this equation a little bit just to try and figure out what some wavelengths are and things like that. Okay? And so here we see this relationship up in the up in this picture up here. Okay, see, we see on this side we have high frequency waves and they have short wavelength, right? So high frequency is a big number, short wavelength is a small number. On the other side you have low frequency, which is a low number, and long wavelength, which means bigger, right? So let's do this again. Low frequency, so as the frequency goes down, the wavelength goes up. And on this side, as the frequency goes up, the wavelength goes down. That's what they're saying here, right? Okay. And, these pictures, the important take-home point, right, is that this visible spectrum is only a tiny, tiny, tiny bit of the spectrum that we can see. Now, we can keep measuring in this direction and into this direction as well, right? And we just keep calling those radio waves, and on this end we just keep calling those gamma rays. And those are the really high energy. So this is high energy on this end, and low energy on this end. Okay, and that's another thing to really remember, right? The X-rays and gamma rays really high energy things, whereas radio waves are not that big of energy. They're pretty low energy. Okay. Now you might see something like, oh, this is where the microwaves are, and well, microwaves can boil water inside a microwave, and that's true, but you get some special resonance of the water molecules is what's going on. Those microwaves are tuned to excite water a lot. Okay. Now I want to also point to you, so again, this visible spectrum is only a tiny, tiny little bit of the whole spectrum up above. But notice on the visible spectrum that we have two ends of it, right? This is the blue, and the other direction, thankfully my three colors cover these, right? The other direction is the red direction. And this is going to become important in the next lecture when we start talking about redshift and blue shift and whatever. And we define directions. So we define directions on the spectrum using these directions that I just pointed to you, using red and blue. Okay, so if I move to the right, so this is sort of and let me tell you that if you just look up a random picture of the electromagnetic spectrum, it might totally just be flipped. Okay, so I would say that blue equals towards high frequency and energy, and red is towards low frequency and low energy. Okay? Whichever direction it's going. So that's the way to keep things in mind. Whether I'm in, I could still be, remember, it's just an absolute direction. So if I'm up here in the infrared, okay, and I decide to go to the right, I'm in the infrared, so it seems like who knows what. But if I go to the right, I'm going in the blue direction. We could say that's blue shifting. If I go the opposite direction, then I'm red shifting. Even if I'm in the ultraviolet or whatever, it's just that absolute direction. Okay, and this can get weirder because if imagine I'm at the edge of the infrared and I go, let's do the blue here. Come on. So I'm up here by the colored spectrum and I go towards the, I don't know what's going on. So I go towards the right. Well, I can shift into the red, but I'm going in the blue direction. Okay. So again, just think about it in that way. Towards high frequency and energy is the blue direction. Towards low frequency and low energy is the red direction. Okay, and there's lots of different representations of this out there, of the spectrum that you can look at and trying to understand what falls into what. Okay, and I recommend taking a look at a couple of them. One that I really like is the one that is on one of my favorite comics, which is XKCD. There's some pretty funny stuff in here, right? So this tells you where all kinds of things are, like slinky waves and the wave, like that happens at a stadium. And here's the main Death Star laser. What else are here? Mail order X-ray glasses, just pretty funny stuff. It is accurate, I would say, absolutely accurate below the blue line, and above the blue line I can't really speak for it. And there's even some pictures of spectra and things like that. So anyways, take a look at this. There's some funny stuff on here, but we'll move to the next slide here, which is to talk about something called stellar spectra. Okay, and for reasons that I'm about to get into, well, reasons that I'm not going to talk too much about, we often see spectra from molecular processes that are going on. And, all right, so I'll talk about it a little bit in detail in a second. But, so if I have light, let me show you here. If I have light that's coming from some white source of not pure light. There's not just one gas or something going on there. This is actually, in a light bulb, is a vibration of electrons. It's giving off all kinds of light through a prism, and you see all of the different spectra over here. They're spread over the spectrum, and you just kind of see a continuum spectrum. Okay. Now, in the second case, if I have some special hot gas, and, well, the stars are made out of special hot gases. They're hydrogen and helium, right? And if they're hot, what's happening actually is that the electrons are jumping around in the orbitals, if you remember this from some high school chemistry class that you had or something like that. And when they drop down in very specific, at very, very specific energies. And those energies come out when we look at the line. So what happens is the light comes through here, and when we spread it out, all we see are these specific emission lines, right, at different places. I just painted over an orange one, and on the other end over here, there's a blue one. And those lines relate to, and I'm not sure which one's which, but they relate to specific electron energy jumps in specific atoms. Okay, so they don't really overlap very much. I could tell you exactly, if I knew the number of that line, I could tell you exactly what atom that was. And this is amazing because it doesn't matter how far that light has traveled to get to me here on Earth, I can tell you exactly what that is. Oh, that's the hydrogen 1 line. That's the line of hydrogen that comes from the electron dropping from this state to this state. And I know exactly what's going on there. And I'll probably post an extra video, I'm not going to take the time here, that explains sort of how these electron jumps happen. Okay, and you can take a look at it there. Now, this is the emission line spectrum because you have these jumps happening because what you're doing is you're heating up a gas, you're exciting the electrons, and this happens. Now, what happens in the other case is that if I shine some light through a cold gas, that gas gets excited by that light, but it only gets excited in those very specific places. So what happens is that the gas absorbs the light as it comes through because it really likes those excitations, and then you see these gaps in exactly the same spots that you would see the emission spectra. And again, I see these lines in really specific places. There are numbers associated with them, and because of those numbers, I can tell you exactly what kind of atoms they are, and I know exactly where they're supposed to fall. And so we're going to use these spectra a lot to tell us all kinds of stuff about the universe, because it's an amazing thing that we see, and this has everything to do with quantum mechanics. Okay, so we're already starting to butt up against quantum mechanics, and quantum mechanics tells us about how these electrons jump from state to state. The math can get really complicated, but the idea is really simple, and so I'll try and find a posting that talks a little bit about that as we go along here. Okay, and so I think I'm going to end the lecture there, and next week we'll start talking about redshifts and blue shifts and the Doppler effect and how we can use those along with these stellar spectra to tell us all kinds of other things about the universe. Okay, so with that said, I will leave you there. Thank you very much. Remember to take a look at your homework and those auxiliary lectures.